Welcome back. So, we were looking at some initiation reactions with some backstories, right? We ended with this Factor emulsification in the previous class. We the homolysis of water can lead to hydroxyl radical formation when high energy ultrasonic waves are used, as in the case of Factor emulsification, and therefore you need to be careful. And the standard practice is to use an antioxidant such as hyaluronic acid, which can handle the hydroxyl radicals during the process. Okay. So, this is where we stopped, and then I think I mentioned one more example, but did not take it forward. Shockwave lithotripsy, right? With the experience of the previous class, I went and checked up what lithotripsy is. Litho is supposed to be stone, and tripsy is supposed to be rubbing, and therefore kidney stone removal by attrition is what this is. Shockwave lithotripsy, breaking kidney stones through rapidly pulsed sonic waves, a very standard practice nowadays. And please take a look at that video for a few minutes to familiarize yourself with the process. Okay, so you're all done, right? I was just working out your attendance along. Okay, so now we are familiar with, all of you are familiar with shockwave lithotripsy aspects. These three are also there. So it is known that this procedure, or rather using ultrasonic waves, can cause cytotoxicity through animal studies on animals and so on. So be a little careful. But I guess they take care and so on and so forth not to operate in this range. However, this is a possible outcome, therefore you need to worry about it. The other place where you need to carefully consider the effect of reactive species is liposome preparation. Okay. During liposome preparation, the ultrasonication is a very standard step. When you do that, you're going to generate a lot of reactive species. So be careful not to destroy the liposome chemical structure through the reactive species that are generated. Okay. Very standard practice in the lab. The lipids are sonicated during preparation of liposomes. Need to be careful for possible effects of generated reactive species from the ultrasound. Okay, any questions or comments? Yes, the shockwave lithotripsy is they use an ultrasonic wave to disrupt the stones. The RS are reactive species. How are they related to lithotripsy? Okay, when you generate these, when you use these ultrasonic waves to break open the stones, it's very likely that you're going to generate RS because of their interaction with the cells. If you do that, then there's a possibility of cytotoxicity even. So be a little careful. Hopefully they would have taken care of all these things, but needs to be looked at. Okay. Yeah.
When we use ultrasonic to break these kidney stones, it might also affect the cells in the kidney.
Certainly,
should we be more worried about the cell disruption due to this due to sonication, or should we be more worried about the generation of reactive species?
Cell disruption due to sonication occurs at a much higher level of energy, the frequency and so on and so forth. So people won't operate at those levels, especially in use for treatment and so on and so forth. They'll take special care not to operate in those regimes.
What frequency
I think they run into megahertz or giga ultrasound, right? What's the speed of sound is, can you calculate 340, let's say 340 meters per second. So you that's your velocity. So you get your frequency from there. That is normal sound. Ultrasound is a few fold higher than that, I think. I'm trying to recall the number that I saw, but I don't, for the Factor emulsification.
Since the ultrasound
Can,
is
can you
not,
check the number, somebody?
since ultrasound is not really audible to us, it must be about 20 kilohertz.
Certainly, certainly about 20 kilohertz.
So like in that case, like won't it be enough to disrupt the cells, or do we need more? Like
Your idea is not to disrupt the cells.
yeah,
Your idea is to keep the cells intact, but disrupt the stones, disrupt the whatever calcium, magnesium deposits in the kidney, right? So it is I think it is localized from whatever little I know. It is focused and it is done in spurts. It is not a continuous stream. It is done in spurts and at energies that can break the stone but not disrupt the cells. That is definite. They will not get into disruption of cells because that is destroying the basis, right? However, in the range that you use to disrupt the cells, you can generate reactive species. Be careful about it. They must have handled it because this is a non-invasive kind of procedure, right? You don't cut open. So there is no way that you can protect the surrounding cells and so on and so forth by antioxidant solutions. In the eye, okay, you can at least topically administer some antioxidant solution. They do, containing hyaluronic acid and so on and so forth. That takes care of it. Here, I don't think that exists. I don't even know whether they look at the damage. They kind of work in certain ranges. My guess, I don't know. My guess is that they work in certain ranges and take the damage as what is it called, collateral damage or whatever. But not much should happen. If that has been happening, then it won't be an approved procedure. It is leading to a lot of this, but this can happen. So be careful with it. Is what all I'm saying. Similarly, there used to be these oxygen bars and so on and so forth. I think we talked about them, right? Pure oxygen, it feels great and all that. Don't go on for long because that can cause a good amount of damage to your lungs, right? Including fibrosis and so on. So that is what we're talking about. Any other questions, comments? Right. Okay. In practice, there are various things, although they may not have recognized that reactive species is causing these things. By trial and error, they would have figured out some range to work in, which is usual practice. So usual practice in engineering is to design, multiply things by 3 and then build, right? Something like that, yeah. So, but if we can reduce that, that will be good. Safety factor, okay. Something like that, okay. Okay, any other questions or comments? Okay, so now let us get on to the second set of reactions, propagation reactions. The whole idea is to give you some common or some useful reactions, introduce you to that. Nothing beyond that, and we do that in the form of some stories, if at all. Wherever I could find stories, I included stories. Quite a lot of effort finding stories there. Okay. So quite straightforward to see that if free radicals are present on both sides of the reactants and as products, then it's a propagation reaction. One is getting converted to another, right? Hypochlorous acid has significance in water treatment. We have already seen this earlier, Hochul and so on and so forth, right? And so this is one reaction with hypochlorous acid and superoxide, giving you oxygen plus chloride plus a hydroxyl radical, which is quite a common occurrence during water treatment. Okay, superoxide gets generated by some means and HCl can react this way, okay, or a possible reaction during water treatment. The Second order rate constant is of the order of 10 power 6, 10 power 7, 7.5 into 10 power 6 per molar per second. Some of the widely found reactions with the hydroxyl radical are actually propagation reactions. Okay, they get formed, and a lot of important reactions that involve hydroxyl radical are all propagation reactions. We will look at some. The types of reactions could be hydrogen abstraction. The hydroxyl radical participates in abstraction of hydrogen from a certain polymer, let us say. Okay. It could be an addition reaction where it adds various things. It could be an electron transfer reaction, and so on. Okay. So, these three kinds are common ones. There could be other types too, but these are the common ones: hydrogen abstraction, addition, or electron transfer. Writing that down. Let me fill in. Now, Abbas is here, Jashwin is here, and Praveen is here. Oh, good, 100% attendance. So, Jashwin, you took care of, you got a note or something like that, is it?
You did get one, but they only told you to get back. Oh yeah.
Asked you to get to discuss with me.
Yeah.
The wrong person, maybe. You attend, but take that out of your record. Unnecessarily don't want to. All the records are clean, so there is some error somewhere, and this will happen. It won't affect you. Ultimately, it won't affect you. So, rather, if it does, you'll have to do some running around. That's all. Okay, so let us look at some of these. When hydroxyl radical reacts with ethanol, it abstracts a hydrogen radical and forms water. For example, ethanol plus hydroxyl radical gives you this radical and water. I just want to follow it. If you want to write down, fine, but just following it is good enough. A species with an unpaired electron may add on to another molecule. This is the addition reaction. Right? This is an example of an abstraction reaction. This is an example of an addition reaction. And the additive product, which is also called the adduct in the field, would still have the unpaired electron, right? It's just addition of the unpaired electron. And a very relevant example is that of addition to, what is this? Does anybody recall this? Look familiar? Adenine, yeah, you're quite close. What else could it be? Adenine. Same kind of molecule, right? Yeah, you figured out it was a DNA base, right? So, this is a guanine. Pardon? Yeah. Right. This recall kind of a thing, we're having some fun here. So, I don't expect you to remember this. If you remember, good, very nice. So, addition of a hydroxyl to guanine, a very standard thing that will happen if the DNA is getting affected by hydroxyl radicals, happens like this. This is kind of a representation. Actually, I should have put in a bracket here and put in a dot and so on and so forth, because this may not be the exact place where the free radical rests. It could be somewhere else. I think somewhere here or something like that. But general idea is that it gets added on. Okay, and this can also happen to adenine very well, but this happens to be guanine. And this is G8OH because it gets added to the 8th position and so on. So, okay, you count your carbons like this, right? You miss out the nitrogen, of course. Carbon, you start from somewhere and it comes to the 8th position, something like that. Okay, so this is the addition reaction which can happen. It can cause damage and so on. Guanine is a purine, that's how we all guessed, and this happens to be, this also happens with thymine, which is a pyrimidine. An example of electron transfer reaction, the hydroxyl radical participates in electron transfer reactions. For example, with halide ions, it could be as simple as this. The chloride ion interacts with the hydroxyl radical to form a chloride radical and a hydroxide ion. Okay. That can happen, just shifting of electrons. So, electron transfer from one molecule to the other, and the chloride radical can further react with the chloride ion such as this to form a chlorine radical. Okay. You may not have heard too much about this, but this is a chlorine radical which exists, which can cause damage and so on. Another example is that of NO2 minus interacting with the hydroxyl radical to give you the nitrite radical and the hydroxide ion. Some just view at kinds of various reactions so that you are not surprised when you come across them later. There are some which are very important, which you may not have heard of at all, some radicals. So, we will talk about some of those. Okay. Now, before we get into the next reaction, right, we essentially looked at some hydroxyl radical reactions. Most of them are propagation reactions, most important ones are propagation reactions of these kinds: hydrogen abstraction, addition and electron transfer. We saw an example of each one of them, which happens in the cell, right, and that can, many of these can lead to direct damage. Quite easy to see why this could lead to DNA damage, and then the electron transfer reactions as this. Good. So, now let us look at blood pH buffering. You all know that the blood pH is buffered. It is, there is a mechanism by which the blood pH is maintained at in a very narrow range, right. And let us refresh our memories in case you don't, in case you don't know, you can always pick up, and most of you would know this. This is pretty much the basis for using carbon dioxide in your CO2 incubators. You provide a 5% CO2 essentially to do this and other things which you don't know. We still don't know what all carbon dioxide does, but definitely it does this in mammalian cell culture. Excuse me. So, please watch this next video and then we will discuss. How much more? You finished? Oh, you're rewatching some. Oh, good. Okay, good. You have access to these things. You can watch it many times. Yeah, I was wondering why isn't that guy not crashing the paper bag? I was waiting for him to crash the paper bag from whatever I could figure out from here. Good. So, that is the principle of buffering. Carbon dioxide plays a major role, right. So, carbon dioxide plus water, carbonic anhydrase gives you H2CO3, which there is a balance between HCO3 minus and H plus, which essentially is the play for the pH buffering. Some propagation reactions with the radicals of the bicarbonate buffer system is what we are going to look at, and it involves a radical which is very important, but you may not have heard of. So, HCO3, if it HCO3 minus, if it reacts, excuse me, if it reacts with hydroxyl radicals, it gives you a carbonate radical, CO3 dot minus, and that is a real radical. Okay, that exists. It can cause significant damage, which we will see very quickly. The rate constant for this reaction is only about 10^7 per molar per second. Right. Another reaction, CO3 2 minus, if it reacts with hydroxyl radical, it again gives you the carbonate radical and of course the hydroxide ion. This happens to be 2 into 10 power 8 per molar per second. And the carbonate radical is also formed through other reactions in the body of the cell, right. So, the focus is on the carbonate radical here, which gets formed from HCO3 minus and so on and so forth. It so happens that this carbonate radical is a potent 1 electron oxidizing agent, okay. Huge positive value, E naught dash is 1.78. Okay, you can take a look at the range of values in your reduction potential table, standard reduction potential table. This would be way up. Okay, it would be way up in the sense it can extract electron it can extract electrons. The electrons that are sorry, it can donate electron to pretty much anything. So, hold on, positive, right? From negative to positive is the table. Therefore, it can. Yeah, I was wondering why it was not, the picture was not fitting. The table is reverse. So, 1.78 would be way down, which means it can accept electrons from pretty much anything. Okay, so it oxidizes a number of biomolecules, and it's so powerful that it can even oxidize hyaluronic acid, which is a very powerful antioxidant in the body, cell, and so on. So, be a little careful with it if you're generating this. Yeah.
Is this carbonate, is the carbonate radical also formed when, let's say, we are in exposure of carbon monoxide?
Carbon monoxide poisoning works differently. That is, it binds irreversibly to hemoglobin, and that is how it causes the death and so on and so forth quite quickly.
Like there is no involvement of.
I don't know. That needs to be checked. And with these things, I can never guess. I'm not a chemist, so I cannot guess whether a reaction is possible or not. Whenever I've tried, I've failed thoroughly. So, this is even with during the chemistry courses, with whatever principles they taught us and all that, whenever I try to guess, I failed thoroughly. It exists, but I cannot guess it, or it does not exist whereas I can guess it. In both ways it has happened. Okay. So, I don't know enough chemistry, and probably the principles are not fully codified. I don't know, it may not be fully codified and so on. It's codified to a certain extent, yes, but whether a reaction is possible and so on and so forth depends on, I know it depends on your thermodynamics, and the speed depends on kinetics and so on and so forth, but beyond that, whether it's possible or not, we'll have to see. So, I would check the chemistry of carbon monoxide and see whether the carbonate radical is formed. If it is formed, yes, it could be an additional pathway to damage, major damage, but the toxicity of carbon monoxide to cause death is something else. Okay. The carbonate radical can abstract a hydrogen radical from cysteine, tyrosine, or NADH. These are amino acids, and of course, NADH, you know what it is, right? These are the reactions that involve that. For completeness, cysteine with carbonate gives you a cysteine radical, and 4.6 into 10 power 7. Tyrosine with a carbonate radical gives you a tyrosine radical, 4.5 into 10 power 7. And with NADH, it gives you the NAD dot radical. The rate constant is 10 power 9, very fast. So, all these can happen. And of course, NAD is not going to sit around, it will react, and it can further react with oxygen to yield superoxide. So, it also gives you an idea of interconversion from one to another and so on and so forth. So, it is not very easy to predict what all can happen or what is the fate of a particular reactive species. It moves from one to another and so on and so forth. Okay. Yeah, please, you can take a picture, but use it for your own purpose. Don't upload it anywhere until at least I tell you. So, this is 1.9 to 10 power 9 per molar per second. Okay. So, just a snapshot of some reactions in which this carbonate radical is involved, and this is an important reaction, NADH. Even these are quite important with the carbonate radical for the damage part of it. Writing it down? Okay. I'll wait for it. These are all there in the textbook also, but at various places. Difficult to find. Okay. Thiols. Okay, thiols are nothing but RSH. The R could be anything, and SH. These act as good antioxidants. If R is H, what is it? If R is H, what do you get? HSH. What is that? What do you know it as? Very common something. H2S. Hydrogen sulfide. The one that causes the rotten egg smell from when you pass through our roads and so on and so forth. Outside, inside you don't get that much, but outside, every day I get a whiff of hydrogen sulfide and things like that in my locality. So H2S is a very good antioxidant. In fact, H2S is used as an antioxidant, effective antioxidant in the brain and so on. Good to remember that. On accepting the unpaired electron from another molecule, they become free radicals, so they participate in propagation reactions. The thiol free radicals are relatively much more stable, and therefore they act as antioxidants. Okay. Some of these radicals are so stable that they stay on for hundreds of years. Their half lives are much larger than that. Okay. In fact, people have found free radicals in a long, very stable free radicals when they do research on Earth and so on and so forth. When we were characterizing our biosorbent, my initial work when I joined IIT Bombay, the funding was not very easy and so on and so forth. So I kept writing proposals. I wrote 10 proposals in my first year, and I think my 9th one got funded after 2 years or something like that. And then, so I had to do something. I had to do some research with whatever little money was available from the department. It was not much. So what do you do? Then figured out you can do some biosorbent work, which was big at that time. I still see papers and so on and so forth on copper biosorption, nickel biosorption, things like that. At that point in time, it was quite hard. So I said, let's work on biosorbents. And then there were a couple of MTech students and so on and so forth who worked on biosorbents, no PhD students, MTech students. The first PhD student joined only in 96 anyway, 96 Jan. So pretty much I joined in 93 April. So it used to take that much time. Have I told you the story? No. Okay. At that point in time, getting PhD students in engineering departments was really difficult. Okay. So when Manjula was my first PhD student, when she joined, 5 students applied. Okay, in that round of interviews, there were 2 rounds of interviews every year. This was the December session, so interviews were in Jan to, she joined in the Jan to May session, so the interviews were in November or something like that. Processing was done, 5 students total applied. All 5 were called for the interview. Okay, we were so desperate with 35 of us in the department, and 3 turned up. Okay, offered all 3. Okay, 1 joined. Who happened to be Manjula. She happened to have worked on reactive species. I had already formulated the problem of getting into reactive species, which I will describe in an appropriate chapter at the appropriate time in the course. And then she had already worked on reactive species. She was a biochemist, by the way. Her basic degree was in biochemistry. She was not an engineer. So she joined at that time. So that was what it was at that point in time, pretty much throughout all IITs. That improved significantly in the late 2000s in engineering departments. Our department has always been very blessed. Okay. I've been doing this. I was the PhD coordinator right from the beginning. Okay. I kept that because I knew it was important, even as the head. and we had 10 positions at that time, now 10 HTRA positions at that time. We used to get some 800, 900 applications. So it was quite a task to bring it down because our faculty could support people from various different backgrounds and so on and so forth. We've always had a good time. So the art students were all, top of the cream kind of a thing. Subsequently, things improved. I think late 2000s, things improved in the engineering departments, and they kind of, now it's a lot better. And why did I bring that in? This thing, right? The free radicals, stable free radicals. So we are doing work on biosorbents. Okay. As a part of the characterization, we did an EPR characterization also, and found very stable free radicals as a part of these biosorbents, which were essentially processed fungal biomass. So we Rhizopus oryzus was what we used. I have a couple of patents on that, by the way. Rhizopus oryzus, we processed it a certain way, and then it had huge surface area per unit mass. Therefore, we used it to remove toxic trace metals such as cobalt, chromium, and so on and so forth, chromium 6 and things like that, from waters. So that was our first work. Suhasini was the MTech student who did the work. She is the first inventor on those patents and so on. So free radicals can be quite long lasting. We just characterized it, and it's quite, I had already gotten into free radicals at that point in time as a part of the main research. I didn't realize it was mean, we were just doing it. And so free radical here, free radical there, I was quite kicked. So these free radicals, because they are more stable thiol ones, they can act as antioxidants. So it is essentially a relativity aspect. An antioxidant does not mean it's not a free radical. It can be a free radical, but just because it is more stable, it can be an antioxidant. Good. I think we should stop now. Okay, I'll give you examples in the Thursday's class and move forward. It's about not even a month, but good to start looking at the papers that you want to pick up. Of course, we are not covered too much. We'd be doing some of these reactions, yes, and then we'd be looking at ways of measuring the reactive species, and then look at how they are involved in the signaling of this cell. So an essential part. So those would be the basic ones. And then after that, I'll get into my research, which is more specialized. So with these basic things, start looking at one, which area you want to focus on for your critical literature survey. Second, keep your eyes and ears open as to what you can, how you could leverage reactive species for your own ends. Okay. Just start. Most of you have done the CFA exercise, so you know the process. It's all a very confusing process in the beginning. That's a part of any creative process. Okay. Creative process is when things come together, it's great. Going through it is a pain, always. But that's what makes the best contributions. Okay. We'll continue on Thursday at 10. Any quick questions, comments? In this case, the learning is that much deeper, and creativity is the highest level that you can reach in learning. Okay, people, we'll meet on